I was invited to speak about the impact or the role of animal movement in disease spread, and particularly in the efforts to control disease. And the reason is that we've been working for quite a while trying to evaluate the role of surveillance in or the impact of surveillance in outbreak magnitude, with particular focus on classical swine fever. But the way we've been approaching these studies could be applicable to pretty much any disease that spreads slowly. We are talking about a low virulence classical swine fever virus. So when I started thinking about the factors that affect disease spread and the role of transportation, we have several tools that we can look at. And the tool number one is the documentation of past outbreaks. And when I mention this, I specifically think of the Netherlands outbreak in 1997, 1998, and the UK outbreak in the 2000 for classical swine fever. There are lots of experimental studies on the role of transportation in disease spread, not just for classical swine fever. There are articles also, and review articles, that have elicited expert opinion on the role of animal movement on disease spread, and there are some results on modeling of disease spread that, of course, apply all the items above. Obviously, what you get from a model is as good as what you feed the model with. So the past documented outbreaks and expert opinion have been critical, and some of the experts that we've used in disease modeling are in this room. So if you have issues with the parameters, we can discuss that later. The historical data indicates that the major players in the CSF outbreak in the Netherlands and in the UK were, number one, the transportation of apparently healthy pigs to other locations. So it's not just transportation. The big issue is when you transport pigs that seem to be healthy and are not. Then the contaminated returning transport trucks and transport equipment. Sometimes for disinfection of the transporting equipment. In this case also, cold temperatures help preserve the virus in the environment, specifically in those in trucks and transporting equipment. And soil feeding has been another factor that contributed to these outbreaks. There are experimental studies with movement that look at movement of animals and how these animals, through secretions, contaminate the livestock trucks and transporting equipment, and it's proven that on experimental setting, these animals can infect other susceptible animals. And there is a publication in 1998 of a panel of experts, 43 experts in the European Union, that tried to address the role of animal movement in disease spread, not just for classical swine fever, but for foot and mouth disease, African swine fever, and other swine diseases. And these experts have scored the factors that were important in disease spread. And the number one is importation of livestock. Importation in the sense of moving livestock into your premise. The number two top score was the returning trucks that are infected and they are not properly cleansed and disinfected. And number three is soil feeding. What we've been working with is we're trying to address the value of surveillance, and in doing so, we try to mimic what an outbreak will look with surveillance and without surveillance. And we used the National Animal Disease Spread Model. That is a complex model that requires parameterization and animal population data, but we also have used basic Excel SEIR models to try to model disease spread. Basically, we compare two scenarios. One scenario with surveillance, the other scenario without surveillance, which is basically let the animals move. don't apply any measures to try to detect and see what happens. And then look at the relative difference between those two scenarios. For parameterizing the model, we looked at the 6 production types that the previous speaker well described: the finishers, the nursery, the growers, and some more integrated production sites, farrow to finish, farrow to grow, and farrow to wean. And we have used some transportation rates, direct and indirect contact rates, based on expert opinion. And so our highest contact rates were the farrow to wean to nursery, which is basically a movement of 7 times, approximately 7 times in 10 days. Then the farrow to grow to a finisher, and then the farrow to wean, and farrow to wean to a finisher, and nursery to a finisher. All the other combinations had a much lower direct contact rate. We also included the possibility of aerosol spread. So in that sense, this scenario could somehow compare with PRRS. We used and we mimic indirect contact of fomites via the feed track, dead track, live hull, and male track. Other parameters that we considered were that once a unit is detected, the detected units were destroyed, and the zoning consisted of a 2-mile zone around the infected premise and a 5-mile buffer zone. And we decided to model with vaccination because we believe that in the case of an outbreak in a state, in a largely populated state like Iowa, that might likely to happen. And we hope that there would be a vaccine by then that would provide protection in 5 days and lifetime immunity. And that we assume that this was another assumption of the model, that we will start vaccinating after 2 units were detected. So this is what we found. And this is just comparing a scenario with and without surveillance. What we found is that when we don't use surveillance, the outbreak is approximately 3 times larger. And that the following factors are mostly responsible for disease spread: the proportion of animals that are subclinical and get moved, the proportion and frequency of animals that are sent to slaughter, because that is a way to sort of control spread, although the returning tracks, if they are contaminated and not properly disinfected, could be perpetuating infection. And then there are a bunch of items that are specific to surveillance, such as the proportion of samples that are included in random surveillance and slaughter, or the proportion of laboratory samples that are randomly included in surveillance at the laboratory level, the probability that a practitioner or a producer or a diagnostician will think CSF and will actually look at testing for CSF or for the disease that we're thinking of. And not only that, but when we have a case of disease that has atypical signs, that is more of a syndrome, where what you have is unthrifty pigs that are not doing well, that are depressed, that may have hyperthermia, that looks pretty much like anything, how rapidly we're trying to do differential diagnosis and rule out concomitant infections, which is part of what happened in past outbreaks. They thought of a certain disease, they tested, it was present, but it was concomitant with CSF. And so the fact that there was not a panel testing delayed the reaction, delayed the response. So the question again is, what is the impact of transportation? And again, transportation by itself is not the problem. It's the transportation of animals that are undetected. It's the transportation of undetected infection. The transport of animal to slaughter is a way of controlling it, but when we come back with infected tracks and we don't apply biosecurity, that's another issue. And so we ran another scenario, simply just to look at what would happen if we were able, in a hypothetical scenario, to reduce animal movement. So what we did is we took the model with surveillance, the same rates, We run that scenario, and we compare it with two other scenarios. Scenario number 2 will be what happens if we reduce the original rates to half, to 50%. Are we able to reduce movement to 50%, and what would happen? And then a very extreme situation. What would happen if we could reduce movement to 1/10 of the original rate? And these are the results. So this is a map of Iowa. This is the original contact rate. And the result is that we have a very extended outbreak, which you can see here. What I'm trying to show is that you have a bunch of premises, of buffer zones in the borders. And what this is indicating us is that this is not an outbreak that is limited to Iowa. This is a multi-state outbreak. So it's a very large, it's a runaway outbreak situation. What we had here is a mean of 650 premises detected. A mean of more than 1 million animals that have been destroyed, and a duration of the outbreak that is almost it's almost 2 years. So it's 22 months. That is with the normal transportation rates. When you reduce transportation to a half, this is what you see. And it's really not as significant as we need it to be, considering the impact of what could mean reducing transportation to a half. It's almost impossible. And the truth of the matter is the outbreak is still extremely large. And you still have all these units indicating that you really have a multi-state problem. Now, when you go to the other extreme of reducing to 1/10 of the original rate, you have a much smaller outbreak with only 18 units detected or premises detected, 24,000 animals, and 200, so less than a year, 8 months outbreak duration. That's what it would take to control the outbreak. So the question is, does it even make sense to think about reducing animal movement? I mean, can we really do that? Very likely not. And we know that very well now after our previous speaker showed us how animals move and why they need to move. So what could be the focus? It could be to try to shorten the detected phase, to try to focus on early detection of disease management, management of the animals that are incorporated to the new farm, the receiving animals, biosecurity of the animals, biosecurity at the level of transporting trucks, and any others that you could think of. So the overall conclusions are that there are a lot of factors other than transportation or involving transportation that affect the control of the disease. Movement is very important, but specifically movement of undetected individuals, undetected infected animals. So if we could enhance detection by enhancing the awareness of producers, practitioners, diagnosticians, if we could consider syndromic surveillance and run panels of tests to rule out disease, and therefore manage the disease better before we transport individuals, that might be a way to control the disease. And specifically look for diseases that have no specific symptoms. So when you have a syndrome, that is when we need to actually define what the problem is. If the disease is rampant and clear and dramatic, we know that we have a problem. The problem is when we have a bunch of unthrifty animals with no clear symptoms, and we keep sending them away without taking much action.